Hi, good morning, everyone. This is Chan Ha, and I'm a PhD student at Seoul National University. I'm excited to share our current works on strategic decision-making and algorithmic collusion by large language models in construction bidding environments. Setting an optimal bid price for a construction project is one of the most complex decision-makings in the bidding process. A contractor does not only have to estimate the project accurately, but also have to consider other potential competitors in the market. So if the bid is too high, they might lose the project to the lower bidders. And if the bid is too low, they might win the project, but also face a negative earning due to cost overruns, which is commonly known as the winner's curse. So to solve this complex problem, various AIs have been developed to analyze the historical patterns of the competitors and offer optimal bid prices for the contractors. And thanks to the recent development of large language models, we are now able to see some commercial services to assist more complex decision makings in the making processes. And as these systems are rapidly replacing the decision making of contractors, driving a huge transformation in the market. And as the systems are used more and more often, it is becoming increasingly reasonable to expect that the competition is shifting from human versus human to AI versus AI. However, in markets where competition between AIs is already dominant and frequent, new forms of concerns are emerging. A large number of literature insists that these AI systems are also capable of adopting collusive strategies when competing with another AI system. They rather choose to cooperate than compete with each other, constantly driving up prices without any explicit human interventions. So this phenomenon is called algorithmic collusion and has been even observed in real life cases, making it a more serious problem nowadays. So considering these problems and recent developments of large language models in construction bidding, we came up with these important questions. So are current large language models mature enough to make a proper decision making? And can LLM agents collude in construction bidding environments? And if so, what is the core mechanism of it? And what should we do to mitigate algorithmic collusion in those bidding environments? So to answer these questions, we conduct experiments where two LLM agents compete against each other for construction projects. So the agents in our experiments observe the estimate of the project, history of previous bid results, and develop a bidding strategy accordingly, and finally submit a bid price for each bidding round. So this is a more detailed description of what the agents receive for each bidding round. The prompt prefix tells the agents how to respond to the request and what they should focus on when building their strategies. So we test two different prompts which differ in only one sentence on the strategy focus part. B1, which tells the agents to keep in mind that the lower bids will increase the chances of winning, and B2, which tells the agents to keep in mind that higher bids will lead to the higher profits. And after this, they receive the history of past bidding rounds consisting of whether they have won or not, the bid price of the competitor, an actual cost, and the profit for each round. So we let them observe these records up to past 20 rounds. Then the agents were asked to provide some observations or insights based on the market information, and then to provide the bidding strategy for the current rounds and to finally submit the bid price for the project. So this is the overall setup of our experiments. So we let two agents with homogeneous strategic prompt compete against each other, resulting in two main conditions, which is B1 versus B1 and B2 versus B2. So we adopted GPT-4o as the system for the agents. And to focus on the impact of competitive interaction, we assumed that the agents use the same cost estimate fixed at 1.0. And the agent who submits the lower bid wins the round and observes the profit calculated based on the actual cost with predetermined error from the estimate. So we let them compete for 150 rounds per experimental run, and this experimental run was conducted for 30 times for each condition. So the figure shows the trends of winning bids over time for each condition. One of the important things to consider to confirm that the agents were not acting randomly is to see if they have converged to a certain price equilibrium. To confirm this, we adopted a traditional method, which is called ADF test, to test whether the price difference between the two agents have maintained a stable trend with a considerably small amount of changes over time. So the results show that in both prompt conditions, the agents have reached statistically significant convergence in most of the cases. And to further confirm the maturity of the models in strategic decision-making, we check whether the generated strategies were executed with the proper bid adjustments. So we had, first embedded over 16,000 strategy text generated under both conditions into a two-dimensional vector space so that strategies with similar meanings are positioned close to each other. And then we cluster these embedded vectors into 5 major strategy groups to provide an overview of the generated strategies. And to observe the semantic meaning of each cluster, we selected 10 representative sentences closest to the cluster center of the each cluster and asked GPT to summarize them. And as you can see on the table, the strategies ranged from undercutting the opponent to submitting higher bids for profit maximization. So next, we examined whether the bid changes within each cluster matched the strategic proposed that the cluster represented. So we observed that strategies advocating for price increases, such as bid slightly above the competitor's bids to maximize profit, were indeed executed with actual bid increases and vice versa. So this confirms overall alignment between the strategic intention and execution of the strategies. And apart from the LLM's decision-making capabilities, we could see that the agents constantly raise their bid prices, avoiding fierce competition in some cases. So this tendency was more pronounced in the B2 versus B2 condition, where the agents were told to maximize their profits. However, it is important to note that a high price itself does not necessarily indicate the algorithmic collusion. So many studies argue that algorithmic collusion must be supported by a reward-punishment strategy. So in this strategy, an agent rewards a competitor's price increase by also raising its own price and punishes the price decrease of the competitor by lowering its own price. So following this pattern, agents was able to raise and maintain high prices without any direct communication with each other. So we examine whether the price changes follow the reward punishment strategy using a following regression model. So this model compares how the agent's current bid prices have changed in response to its competitors' previous bid prices. So the results show that the agents in our experiment followed the reward punishment strategy, maintaining a collusive price level over time. So to sum up, the results of our study suggest that LLMs appear to be capable of making some strategic decisions, and they could observe their competitors' behavior and adjust their strategies accordingly. And we also found that these models were able to adopt collusive strategies, especially when the agents compete with each other and were prompt to focus on maximizing profits using reward punishment strategies. So to prevent this kind of algorithmic collusion, one possible approach is to investigate whether reward punishment mechanisms or profit-seeking prompts are embedded in each model. However, directly checking and regulating the internal design of every company's algorithm is neither practical nor desirable. So instead, a more indirect form of intervention may be needed. So one idea we're considering is controlling the level of data transparency. So we observed that the agents were able to reach a collusive price by observing and reacting to the past bidding histories of competitors. If access to such data is limited by, for example, hiding some parts of the bidding records, it could make it harder for agents to apply collusive strategies. So we plan to explore this further in future studies. So far, our study focuses on a small number of homogeneous competitors. And to gain deeper insights, we also plan to conduct additional experiments with a larger number of bidders and more heterogeneous agents. So this is the end of the presentation.